So I'm going to give you an overview of NDN. In case you haven't heard about NDN before, this is an NSF-funded project since 2010, where when the NSF started this new program at that time called the Future Internet Architecture. Yet you can see that there's been a while since then. So we have built up many results. My talk today will be, first, I just briefly mention about what is this internet architecture we are talking. That will put NDN in the proper place in the big picture. Then I will mention very briefly the basic concept, how NDN actually works. Like Timer mentioned, it's really particularly fitted for the battlefield hostile environment, but how that actually happened. Later, Alex is going to talk more about the code base and experimentation facilities and security when he introduces IoT environment. So I think our basic goal is to explain, hopefully convincingly, why NDN is particularly suited for battlefield networking, even though the project wasn't specifically aimed at that environment. Just by nature of focusing on data, that the architecture has that property. Timer mentioned that I started networking back in 1981. When I walked into MIT in September, my former advisor, David Clark, handed me the TCP/IP specification, saying that, oh, this is just hot off print, read it. And that's the red picture. Later, we figured we can draw it in a prettier way, so that's resulting in that hourglass. It's pretty simple, right? So look at the transport. It just provides you data delivery, and if you run TCP, it's a reliable data delivery between two end processes. There are many papers published on how you can tuning the TCP's congestion control scheme to achieve the fair or maximum throughput. But nevertheless, that's just between two endpoints. And you look at the link layer, that's just, again, between two endpoints, correspond hop. So the power of internet is really in the middle, in this narrow waist, because it provides any host to any other host data delivery, albeit unreliably, best effort. So the narrow waist actually has the widest deployment, because for any device, if you claim it's connected on the internet, it must have the IP supported in it. It might not run TCP. It might not run Wi-Fi or any other particular link, the layer 2 protocol, but nevertheless, it must run IP, so it can exchange data with other things on the internet. So why we built this host-to-host, point-to-point data delivery, because back then, when I got into networking, the whole concept was connecting up to remote host. The most precious resources by that time was computation power. And that's what you share. You log into some remote machine through the DevOps, actually, to utilize the computation there. But that has been almost close to 40 years now. So what we have today, this end-to-end host-to-host data delivery has led to this a flourish of all the new applications. I must add, that is, the new applications are not only enabled by the TCP/IP protocol architecture, but more so by the technology. And I often talk to people like Dave Clark, saying that you people, being visionaries, were brilliant, developed this protocol stack. Nevertheless, without the Moore's law, there would not have been such a tremendous success. It was a technology that put the cheap computation devices in everyone's hands, actually several in everyone's hands, and that enables the flourish of the applications and hence the rapid growth of the internet. But what has changed besides those applications? The demand on the networking side. These days, who cares about remote login? When I talk remote login to my new students, they think that there's something bizarre concept they have never heard before, right? Nobody wants to share computation resources. Instead, you want to run your Facebook, Netflix, lately the augmented reality and the many other new applications where the application merely exchange data, and they don't really care which end nodes they connect to. As a matter of fact, that becomes a difficult problem. So why it becomes a difficult problem to figure out which end host the network layer has to connect to? There's a problem that you cannot see from this hourglass picture. So what is that problem? That's a different namespace. Applications, we all know the usernames. If you don't know what the names are, think about the URL that your web request sent it out. That the URL started with some DNS name, facebook.com, and the slash, and there's some other parameters in the URL. So fundamentally, that's how the applications think, that I send out a request for data, and data should come back. But then nevertheless, below application protocol, all you have are the port numbers and the addresses. So therefore, there's entirely separate orthogonal namespace, and you have to do something to bridge the gap. And of course, for people who really play with network, you know that below the IP layer, there's yet another namespace. That's the MAC layer, and they run the MAC addresses. But let's forget the the MAC layer and just think about the issues with the first two, the mismatch. So why the different namespaces really matter? Because think that, like I said, you want to look at your Facebook, your friends posting whatever. You say that, hey, your application size, give me this piece of data. And what happens is that the network doesn't understand what you want. So therefore, there is some shim layer that will have to translate the names into an IP address. And after you get the address, you set up a TCP connection. And all of this is really cause the issues. What are the issues? One, it's not you run your apps, you have to get an IP address. How do you get an IP address? You need infrastructure service support. You have to have DHCP server installed somewhere, so you get the IP address, you're connected. Now the next thing is that when the application said, give me this piece of data called X, then that X has to be translated into some IP address. Why? So you require the DNS, another infrastructure service support for you to do the translation. And now you can set up the TCP connection. And everyone knows that TCP connections don't work that well if you are in a very hostile environment. You have heavy packet losses, and not to mention that if you're in a mobile environment, your address actually changes over time. That will be much worse. So those issues has been long recognized. Those complexity and dependency are purely due to this mismatch between what the application is doing and what the network actually provides. So back 11 years now, there's this guy, some people, or most of you may recognize the name, Van Jacobson. And he gave this Google talk and saying that there's really a different way to do networking. Whoever interested, you can still listen to that talk. It's quite interesting. But if I just summarize the talk in one sentence, it basically says, let's do networking by what applications are doing, just like you name the data and fetch the data directly. Now, it's at the network layer. At the network layer, you do exactly what the web is doing at the application layer. You just send out requests for data, then you get data back. And in this way, that will make a picture look like this. You still have with the hourglass protocol architecture, because there have been theoreticians, they actually proved to say this hourglass protocol stack is the right one. Above the narrow waist, there are so many different applications, and below the narrow waist, there are so many different technologies that can connect any two nodes together. So therefore, you need a common protocol in the middle to bridge the upper and the lower. So conceptually, it's a simple change. Always shows on the right hourglass is that let's just bring the application names, like URL, for example, down directly to network layer. So this actually shows the three basic changes in this conceptually simple change. For one is the network layer, get rid of IP addresses. What you use the name directly from your application. Everything's built on the web these days, and the web uses URL. That's a name for HTTP objects. Let's just use that directly at the network layer to fetch the data. So I mentioned, so the second thing is that what you name is you name the data, no longer you don't name host anymore. And the third thing is that once you name the data, you have to do something different than what you can do with IP packet. For IP packet, because now we name addresses, you can put a destination on the packet, you say go, right? You just shoot the packets out like you're shooting a bullet. But when you name a piece of data, I don't know, your Facebook page, the data doesn't go anywhere. So therefore, what you have to do, just like a web, you need to send a request for data, and data will come to you. So for the left side, IP is kind of a push architecture. You shoot the packets out. And on the right, NDN is a pull architecture. You actually send requests to get data. And later I want to explain to you how this pull architecture provides you so many advantages. And so that it's really fundamental. Now, with this, that will bring down the change to the network layer. You cannot use something equivalent to IP because you're going to fetch data. So at the network layer, or really at the network layer, NDN defines two types of packets now. For IP, because just shoot, doesn't matter what's in the packet. You just have one IP packet header. Now you need two. One is equivalent to the HTTP request, and the other one is equivalent to HTTP reply. So just like a HTTP, right? You care about the names, and then what you get back is the contents. But you can see that, you can see there's one fundamental difference between NDN packet, this is at the network layer, I want to remind you, and HTTP. That big change is crypto signature. So NDN size, the publisher, whoever produces data, will produce the bits and then immediately create a crypto signature that binds the name to the content. And this is a built-in security at the network layer mandated by the NDN architecture. This is one of the two fundamental differences between NDN packets, NDN data packets, and your HTTP reply. Of course, there's a basic difference that HTTP is at the application level. I want to remind you again, we're talking about network layer packet exchanges. So the number one, data is secured directly. Number two, data is immutable. Data is immutable. That is, you produce a piece of data, and that's it. You do not change it. When I prepared this presentation, of course, I revised it many times till the last minute. What happened to a revision? you put a version number as a part of the name. So therefore, all the different versions are uniquely named. Think of this question, like you want to look at today's news, you say CNN.com. Now it brings back this page, lots of contents. Now if you ask the same, you send the same HTTP request 5 hours later, I believe for sure they're going to bring back a very different page because the CNN updates their contents pretty frequently. Say, can you, say, look at the CNN's website from yesterday? You cannot, because that the same URL actually named different data. That is an example of immutable data, mutable data. And here, what I'm talking about, NDN is immutable. I think this will be a very useful property in the battlefield things. In the battlefield these days, we have lots of sensor data produced at different times. You really want to uniquely name every piece of data produced at different time so that you can capture the situations precisely. Now, once you remove this incongruity between the application naming and the network naming, what's the benefit? So this is a picture I showed you earlier, and here's a picture we have now with NDN. When the application said, give me the data X, the network will say, sure, I will find it, the nearest copy of X and bring back to you. Why you find the nearest copy? Because you no longer care exactly where, from which device you get the data. You can always verify it because the data carries its own signature, and that cannot be changed without detection. Now, exactly where the network will find the data. Many different possibilities that I'm going to explain to you later. But in one word, all the devices can be potential sources for the data you are requesting. So just take the word as a given. Now I want to show you that you have many advantages once you remove that incongruity between application and the network. You no longer need this DHCP server to get your address. Forget that one. And because you don't have an address, you no longer have to worry about the translation from names to addresses. You just use the names directly. And what about reliable connectivity between the two ends, whoever produces data, whoever wants it? You no longer require a reliable, stable connectivity because NDN has this nature that they can just fetch data in the most resilient way. It doesn't even require both ends to be connected at exactly the same time. By the end of my talk, you can see how that happens. The fundamental trick is that NDN use names. Okay, how use names give you all this power. So I give you a very simple example. Say that this is my presentation file. You may want to look at the file to see how many more slides you have. Today, if you want to get the file from my laptop, can you? Physically, you can. I have Wi-Fi, you have Wi-Fi. There's nothing about the signal cannot reach each other. It can reach very far away for Wi-Fi. But pragmatically, you cannot do it because you haven't learned what is my IP address yet. In NDN, you no longer need the address. What you have is you can put the NDN packet directly on top of Wi-Fi, the layer 2. So if Bob is interested in discover whatever available within its one hop Wi-Fi, it can just send out this discover request. And given that I'm willing to share this thing, and I'm going to make my data available. So I want to explain to you what this discover really is. You can define this keyword discover. We call the naming convention. That is established keyword that has specific meaning to the applications. Convention may be a strange word to you, but think about like you go China and you drive. You have a problem, you don't have any problem because China follows exactly the same the traffic signal convention like in any other part of the country. Red means you stop, green means you go, yellow, well, up to interpretation. But that's a standard convention shared worldwide. So in NDN, basically says that, look, guys, convention is everywhere in life. And you can really utilize that concept to simplify the networking. Then I said, I'm willing to share my data when my laptop heard that request for, say, hey, any information available. I'm going to send back this reply to say, okay, you want to discover something? Here's my slides I'm willing to share. And you'll notice that at the end, that a little dash V10, that's what I meant by, every piece of data is unique. That's my latest version number. If I decide to make another tweak tonight, there'll be a different name. It'll be version 11, so that you can uniquely identify every published data. And in my reply, of course, I'm going to provide you more information because I want you to get my data. I would say that this whole file is very large. It's about 10 megabytes, and I chop into how many packets. So this is just to facilitate your fetching if you need. And maybe Bob is not interested in fetching that big file. Look at that. Oh, 10 meg. Well, leave it for now. But it can cache this reply in the local cache. Why you can cache it? Because this is not a particular reply sent to Bob specifically, like an IP packet. IP packet will send to Bob's IP address, and nobody else can make use of that. I'm talking about at the network layer. At the network layer. The network layer doesn't know what's inside in IP. But in NDN, network layer directly uses application name, so the network layer knows that, oh, this packet is labeled by this many bits. Does the network layer understand what this is? Of course it doesn't. But nevertheless, it knows the bit, this, 120 or something. And because the data is signed, so this data can be potentially useful to others. Just continuing on the example, say that there's Alice, some distance away, and so therefore you can see Alice is not within the Wi-Fi coverage area, but there's a Bluetooth reachability between Alice and Bob. So Alice says, I want to discover what's available. And when the request reaches Bob's laptop, Bob's laptop said, oh, I have something that matches your prefix. This is the same like today's IP network. When the router forwards packets, it does longest prefix match. Right? It doesn't have to have the whole name, but rather if the prefix match, NDN believes that, okay, this is the data potentially satisfies your requirement. So therefore, Bob can really just grab from the cache and send to it. I want to make it very clear. This is the network layer. Bob's laptop is not a HTTP proxy. Okay, it's not like what we do today. You have an application layer overlays. No, none of that. It's just at the network layer, you get a network request, you send a network reply. Now, say that Alice actually is interested in fetching this file. Okay, how it gets it? Like I said, the file has to be chopped into many pieces of network level packets because no network level can send a file like 10 megabytes as a whole piece. Network level, you have to worry about the multiplexing, right? There are so many streams of packets going around that if you send a whole gigantic chunk, of course you see this only one hop, but the same protocol runs in global scale as well. So routers cannot store a packet of 10 megabytes. So therefore you chop into many different pieces. Now exactly how that looks like. I said interesting data carries the names. So the names is actually at the packet granularity. Here, you can see that the complete name for the first packet actually is not only version 2, but also segment 1. And this replied, the previous replied thing that Alice got will allow the Alice to say that if I want to fetch the file, I'm going to start from the first packet. So these are the naming conventions. Your applications don't have to worry about that. Then the system will automatically remember the different versions you saved and chop them into proper segments and assign each segment. So whenever a request for any segments comes, you just look at your storage, grab one, and set it out. So when Alex decides to fetch my file, you can see that the request will go through Bob and get forwarded to my laptop following that request. By the way, if people have questions, please feel free.
Yeah. So in this example, you have a way to get to your laptop. But what if no one knows of the named data packet that you're trying to get to?
So it's really a slide. You can see that I said, Bob remembered, okay, I got this reply. I'm not going to fetch it. It's so big yet. But you remember this reply, and you remember from which interface it actually came from. So therefore, here, when Bob received the request from Alice, and assuming that Bob is willing to help Alice to get the packet, Bob knows exactly which MAC address this request from Alice should go out to, towards where the first reply about data sources.
Okay. So you're assuming that infrastructure knows of the information that's there, and we have a way to get to it. Right?
I want to make it very clear. There's no assumption, but rather this kind of a learning process, right? You hear a packet, you know where that it came from. Think about the currently in the layer 2, there's this Ethernet, the self-learning. For MAC address, they say for any machines, this is plug and play. You never have to configure which MAC address in which direction, because the bridge, the Ethernet bridge, can automatically learn about it. They get a MAC packet, the frame, look at destination. Do I know where its destination is? If you don't, you send to all your interfaces. Now, if you do, that is you observe that someone sent you a frame with the source address X. Next time you see a frame with destination X, you say, oh, go that direction because I saw there's a source in that direction. This is kind of self-learning. And that's exactly what we are doing here. We don't have to configure things, but at this network layer, you can learn about things. You can learn which name prefix is in which interface direction. Yeah. Okay, you go first.
Yeah, but if there is no connectivity any longer between your computer and Bob's computer, then it doesn't work any longer.
Right. So connectivity can change. If you send the interest, it doesn't get a reply, then you know that's no longer there. Then you can try other alternatives. I'm going to explain that later too.
And if Bob is mobile and has limited power supply, Bob might not want to share.
Right. Yeah, I agree. So if Bob is mobile, it doesn't want to share, then it's a separate issue, right? And then maybe there's somebody else want to share. What I'm saying is that if there's a willing people want to do this mesh networking, help each other to get the information, then NDN allows you to do this kind of sharing without configuration. It's all self-learning, yeah.
So maybe you described later, or I think there's this question of how that information is shared and how that learning process happens if there wasn't a request before. In this case, Bob specifically asked for your talk, and then learned, and then Alice gets What if Alice asks for produce token void that Bob has no idea about?
So yeah, the question is that what if Bob never tried to discover anything? And then just that when Alice sends a request, if Bob is willing to help, Bob will forward that request.
So flood that through the network?
Huh?
So that request will be flooded throughout the network?
Well, this kind of self-learning has to be scope limited, right? And later I'm going to talk about in larger scale network how you're going to do things.
Do you have the concept of an authoritative response? So, for instance, let's say Bob sent out the discovery pack and you answer back and said, yeah, I've got version 10 of my MILCOM briefing. And then later Alice comes on and she says, hey, I want a copy of the brief. And he says, yeah, version 10 is what I've got. But in the meantime, you've created version 11. So is it every time Alice asks Bob, okay, what have you got? He says, this is what I've heard, and he forwards an interest further up the line?
Right. So the question is, what if I already create a new version? How you learn about it? This is a toy example to explain how, if you use names directly at the network layer, things just simplify. That you can do self-learning. Regarding how you can keep up with the latest update, I have to tell you that in real networks, things are a little more. You have to do a little more than the simple things, because like when Bob wants to discover things, there could be multiple data available. And then say, I don't know, Mike also wants to discover things, right? So how you can minimize all these packets flooding and exchanges. We actually have a different concept to say that for the local information, you actually do a collection. I'm sitting here, I hear people ask questions, reply questions, I collect them all. And we created this thing we call the synchronization. This is a synchronization of a locally available data set. So therefore, when I hear a request, actually I can send out not just my own information I'm willing to share, but also the set that I have learned. And because you have this local site, so when you send it out, and remember, the wireless is broadcast in nature, right? Somebody else sent out this shared site. I hear it. Actually, I said, I already have an updated version. And then I'm actually going to inform all my local neighbors about this updated thing. So this is kind of mesh exchanges, and they keep you updated. And also, I can be willingly just send out updates on the shared data set. Not to the data itself, but to the names of the data set. Like I said, the new version is going to have a different name. So that's a way to inform others. But there's a way advanced things that in my limited time I won't be able to cover. Okay, whoever interested, there are many different kind of resources on the NDN website. You can dig. Yeah.
I'm just going to say one thing real quick, just to give everybody an analogy between that maybe help clarify some of these questions. The IP protocol itself doesn't provide a notion of the services that we're talking about. It doesn't give you a way for you to discover IP addresses or to map addresses to URLs and things like that. These were services that we will do later. We're talking about here something that the basic functionality. There's still going to be we still have to have services that give you discoveries, maybe in a local environment that is not very large. You can do that by flooding. But if you're talking about scalability, you have to provide overlay. But in general, it's talking about the fundamentals of the protocol without having to deal with the services that go along with it that make it work.
So let's move on. So say that, when Alice sent the first request out, this is asking, Alice wants to get my whole file, right? It's not like just the request reply. You can do same kind of pipelining as we do today. When TCP send data, it doesn't really send one waiting for ACK, but rather you can send multiple. And the same thing here. You can send multiple things out and multiple requests out, segment 1, 2, 3, 4, 5, and waiting for the reply. And I mentioned that when Bob sent forward the request, it remembers where the request comes from, which interface. Now this time is from the Bluetooth. And when data comes back, Bob got the data. It knows, oh, this is where request comes. So therefore, you can send the data out to the interface where the request came in. So NDN, very different from IP. It uses a stateful forwarding. When I say forwarding, you forward the interest, the request packet, so that you remember where the request comes. That's how the reply, the data, can go back. So when I showed you earlier, look at the packet format. There's nowhere that has an address. Both packets carries the data name. So how would the data go back? So interest get forwarded based on the name. The data goes back based on the state that all the forwarders have kept when they forwarded their request. You can think this in some way it accomplishes the functionality like what we call ad hoc networking. But ad hoc networking, as of today with IP, requires some kind of ad hoc routing protocols. Why can't today's IP ad hoc networking get rid of a routing protocol, just do the same thing? That is because if you get rid of routing protocol, there's no state in the intermediate nodes to know where to forward things, because the IP at the data plane is entirely stateless. You get the IP packet, you threw it out, and you forgot it. You don't know where it come, where it went, and so therefore you cannot really do anything without the routing protocol. In NDN, because it's a forwarding plane, it's stateful. You remember about the interest until the data comes back. So therefore, you get rid of the need for the ad hoc routing in small scale and can do this self-learning and perform all of these functions. Now, one more thing about NDN. Again, say that this packet going out, somehow they get lost over this Bluetooth link. Now, what happens? So NDN, just like IP, at the network layer, is datagrams. Although I said I keep state, it only keeps state of where the interest came. When data goes out, I forget it. If the data packet gets lost, it's still the original requester, the end application that need to retransmit the unsatisfied interest. And then the retransmitted interest is going to hit Bob's laptop, and Bob will just get the thing out of the cache and send it again. And this is how you can get really fast and resilient loss recovery, because you don't have to go back to the original server to get the data. So now I'm showing you a different story. Say after Alice get the whole file, Alice went down, taken a bath, and go some other business. Alice, with my file on her phone, become the data mule. So therefore, if on the bus, the passenger's gonna do some kind of information discovery, who has what, and Alice can easily pass my files to share with other people, and I will be very happy to see that. The point is that this is a delay tolerant networking by nature. We haven't done anything different or special. Because the delay tolerant networking only needs two things. One is that the device has to be need memory so you can carry things, become the data mule. And the second is that data has to be identified independent from any locations, addresses. So others, they want the data, they can, as long as they learn the data name, they can fetch it. They don't really care from whom they get it, because NDN data is assigned. You can always fetch my key from UCLA and verify, hey, is that a true file produced by Lixia? And that's something today's DTN still does not have. So we see that NDN names the data, applications will assign name to every packet. Then you can have automatic information discovery at the network layer. Today we do information discovery. How? There's a MDNS, the so-called multicast DNS, but actually it's really just a multicast to a server. The server has more information and sends you back things. Here, because we use names at the application, at the network level. So therefore, you don't need a specialized server to do the discovery. And at the same time, you can do is ad hoc delay tolerant networking. The next thing about using names is that now you can use multiple interfaces. Look at your phone, look at my phone, right? All the phones have multiple interfaces. You have Wi-Fi, you have Bluetooth, you have LTE, and you may have this near field communication capabilities as well. Today, how you can make your device do multi-homing, that is, make use of all the multiple interfaces, especially simultaneously, it's really hard. Because IP assigns one IP address per interface. And by default, your device only allows you to use one interface at a time. It will decide which one you're supposed to use. It's really difficult to say, I want to use both, or I prefer this one over that one. There's no such a capability for you today. For NDN, because your name data is totally independent from interfaces. You can use any. You want to send request out. Do you go Wi-Fi? Do you go LTE? You actually can send simultaneously to both interfaces and see which one actually brings back the data faster. My phone, I use T-Mobile. It's flat rate. You know, it's perfect. I can just utilize Wi-Fi, LTE, whoever bring back the first packet, and the future ones will go to the one that actually works. So how you choose this when you have choices? So NDN has this design-in module called forwarding strategy that makes a decision on how the interest get forwarded. Now, the next thing is that names are hierarchy. We already saw that. Why is this hierarchical names is useful? Because it provides you the application context. Okay, you can see that there's a file produced by me. I'm from UCLA, and therefore, how you verify this, you can reason about it. Whether you trust the key from UCLA, UCS key, signed my key, etc. You can also automate the confidentiality control. You know, say that if I have a private file, I don't want to share with anybody, well, with somebody, but not everyone. I can encrypt the file and distribute the decryption key only to the people I want them to have access. All of this can be automated. The key word is automated. Today, you want to do authentication, you want to do encryption. The difficulties are not the crypto. The theoreticians have all the crypto things worked out. The difficulties in really support security today is the key management. It's a key management. How do you get the keys? Which keys you get? Which keys goes where? This has to be humanly managed. And the NDN can automate that. Unfortunately, I won't have time to talk about that. Alex, going to give you a quick introduction, but I hope that we'll give you some pointers. Whoever interested can look into that. The next thing about hierarchical naming is that it enables name aggregation. Like, look at my file, right? It's a hierarchical. You say, on the global internet, how would you find this file? Well, you don't have to put my file name into the global routing table. Instead, you can just put it, UCLA.edu in the routing table. And then I'm going to just show you this. So that when the request goes to UCLA knows where Lixia is. And then they're going to forward your request into my computer or my storage, and so that you can retrieve the data. So in the large scale, NDN will just do routing, just like today's internet. So the beauty of NDN is that it actually can utilize the existing protocols, like routing. Routing is fundamentally independent from what is the format you use for your network level protocol. Routing basic size, I build a table so that when the packet comes, I know where to shoot it out. For IP, you forward based on destination address. For NDN, you forward based on the name carried in the interest packet. Now, the last thing I want to talk about the names is that names is really the multiplexer. Like I said, anything you want to know about the NDN, about UCLA, the network figures out. Okay, that's where UCLA make their routing announcement. So the interest packet gonna go UCLA. And once you reach the UCLA server, then based on the next components in your name, you do the demultiplexing to different service processes. What we do today is using port numbers to do further demultiplexing. So you have address at the network level, you have port numbers at the transport level, and then you have sequence numbers to tell the application which piece of data this really is. In NDN, it's just in another one name. And that name is bound to the contents by crypto. So advantages, we already mentioned all of this. And I will add one more piece. That is, think about the cyberspace. What does the network do? The network basically ships packets of bits. What are your keys? What are your trust policies? Your keys are a bag of bits. And your trust policies is state in a file. It's also a bag of bits. Today, how do you get somebody's key? You want to get UCLA's public key. How do you get it? Network says, give me an address, I'll send your packet to. But I have to figure out which of the UCLA addresses actually is their key server. So those are all these questions. Yeah, in the end, don't worry, you want UCLA's key, just put the name, throw it out, the network will find it for you and bring data back. Now, I'm going to mention briefly about this stateful forwarding plane. I showed you some functionalities supported by this stateful forwarding plane, but exactly how it works. In IP, for whoever playing with routers, you know that there's the forwarding information base that tells the IP router, give a packet, the destination, where you send it out. In NDN, you have two more pieces of data structure. One is a pending interest table we mentioned before. Every time you get the interest, if you forward it, if you drop it, forget it. You're not going to serve, you're not going to be a forwarder for the data return. But if you forward the interest, you have to remember, okay, where the interest came, where did I send it out? So that when data comes back, you traverse the path, get data back to whoever asked it for. So it's a pending interest table. Another piece is we call the content store. That's just opportunistic caching. When data returned, you can keep it in the content store for long, for short time, depending on whatever the data producer may want you to do. So in the data packet, there's actually information that it says, how long the producer thinks the data will be fresh. Some people say, if I'm doing a conversation, I really don't want my voice to be cached in lots of places. Sure. But you can see that if nothing else, the caching will help you to do quick loss recovery. Right? Very quick loss recovery. So even for that purpose, you want to cache data during a short time period in case the consumer of your data didn't get it. They're going to retransmit the request. They're going to hit any cached copy, the nearest cached copy, and bring the data back. Now let's look at the FIP. This tells where the interest should be forwarded. In IP, this basically you rely on the routing table to build it. But as I showed you earlier, this can also be fed in the NDN network by self-learning. For the exactly the content of the FIP, you can see that there's two differences. One is there's not IP prefix table. It's a name prefix table. There's also a second difference. It's on the right side. For next hop, for IP forwarding, one next hop per prefix. You cannot have two. IP does single pass forwarding. There's so many papers written about doing multi-pass forwarding. That's still a very active research area. Why we cannot do multi-pass forwarding? Worrying about the loops. You send packet out, if it loops back, you have no clue. You have seen it before, you just send it back again, send it out again. For NDN, you don't have that worry because you have pending interest table. You receive interest, you check, hey, is that in my interest table already? And if so, it's a looped packet, you drop it. Now I'm going to show you very quickly how this thing works. So a forwarder can be an official big router, can be your laptop, or you are willing to in an ad hoc environment. You get a request, you say, hey, do I have this in my cache? If yes, you send it back. If not, you say, do I have it in my pending interest table? If so, you just need to remember, okay, this new incoming interface, this interest come, and you don't have to send the same thing twice. If you fail the first two tests, then you say, where do I know where to forward it? And if there's multiple choices, you have to make a decision. All of these decisions will be made by the forwarding strategy based on multiple factors. So forwarding strategy may decide to forward along one, along multiple interfaces, or do simple another, just one hop broadcast out of all the interfaces. So when data comes back, the first thing you check is, did I ask for that piece of data? By looking up your forwarding interest table to see, pending interest table to see, do I have a matching entry? This will prevent anyone shooting data packet to you as a DDoS. If you didn't ask, you cannot, the data will not come. You just drop it. If you find the entry in your pending interest table, I think in my earlier thing, I forgot to mention that for everything you send it out, you actually record the time you send the interest out. So therefore, when data comes back, you can calculate how long it takes. You can do other measurements, like an estimate of your throughput. Measurement has been one of the major research challenges on today's internet because of the stateless nature of the data plane. In NDN, measurement is built in at the per packet level. And then you look at your incoming interface for that interest to say, how many interfaces I've seen requests for this piece of data? Then you just send one copy to each of those interfaces. So this is a multicast delivery. If there are two people ask for the same data, you send the copy out. Again, IP multicast has been a challenge since the late 80s, because my dear friend, Steve Deeren, he did his thesis on IP multicast in 1989. Where is IP multicast today? It's a good question for everyone. NDN, because you have stateful forwarding, you get a multicast built in without doing anything. And then I say you can save a copy. So this is equivalent to this content, the CDN's content distribution network, right? You save a copy. If anyone else asks for the same data, you deliver it. So multicast, the measurement, multicast, and scalable content delivery, it's all automatically built in. Then you can remove the pit entry as this work done. So in summary, yeah.
The question with some of these mechanisms, see the denial of service being prevented by finding a match in the interest table. What if you were to spoof the data and remove the entry from the table before the real data comes? Is that possible to inject?
You talk about possibilities. Yes, everything is possible, right? But you have to have a precise mapping. You have to know there is that request interest with that prefix. And you have to, unless you do eavesdrop, otherwise it's very difficult to get it right. Because the pending interest table entry only stays for one round trip time. When data comes back, it's already removed.
If you inject the data before.
You have to, I think, if you think to do it, you better be able to eavesdrop, you know exactly, yeah, and because the timing is extremely important.
But there's another thing also. Remember, every single piece of data has a signature on it.
Yeah, you can verify. So the router can verify.
To forge it, you have to then crack in the signature as well. Okay.
Does every node check the signature?
That's not required. That's not required. But you can do it as like a background process or selectively and other things. That's one of the remaining open research questions. But it gives you the ability if you want to check. So forwarding strategy, how you make the decisions, it's not just like IP, look up a FAB, you shoot things out. Now the FAB has multiple choices. So the forwarding strategy is going to take a look of the measurement, which of the options actually works the best. And also, you can have policies. Like I said, everything is based on the names. The forwarding strategy can actually be configured with the policies, /DOD, this has highest priority, must be resiliently delivered, you always multicast out or something. And I don't know, /Netflix, you always put in the lowest priority and treat it differently. So forwarding strategy actually has a policies per namespace to allow you to fine-tuning your decisions when your resources are limited. So NDN's secret sauce is all in the names. Once you get the name, shoot it out, network will take care of where you find the data for you. So the question is now how the consumer learns about the names, right? There are basically three ways so far we have tried. And there's how to best to do the name discovery. It's still active research thing. But let me mention briefly, naming convention. We do use it today. All the website with the www in front. Is it necessary? It's not necessary. It's a convention. It just tell you this name leads to a web server. And so the same for the mail server. We saw two examples about naming conventions earlier. One is about the suffix, right? You say you have version number, you have segment number. Another one is about prefix. This is a specialized prefix for you to do the name discovery. So it informs the forwarder. The forwarder sitting in all the NDN nodes. Like how you're going to handle this request. Name discovery by metadata. That's actually what we do today on the web. You say, I want to look up Wikipedia. Look at the page, there are lots of contents. How did you get all the contents? You actually fetched. So when you send a request for wikipedia.org, what you get back is a file. If you look, you can take a look of that file as a basically tons of pointers to the other pieces that should show up on the page, and you go fetch those names. Another example, how you find the information. So I use the example of SIGCOMM 2017, which UCLA hosted 2 months back on campus. We recorded all the things. Now, if you want to fetch the recording, you can do a rough guess, ACM SIGCOMM 17 video. That's a prefix, because you don't know what the longer name would be. But once you send this prefix, the network will send you back the data. It has the exact match of your prefix, but the data, of course, has a much longer time. And this later part is really the naming conventions defined by the application. But once you get this long name, your application knows how to interpret them and figure out how you fetch other pieces of data. Then you can also learn about dynamically generated data by some producers you don't know. That is, like you don't even know there's a SIGCOMM recording. So we say that you can do broadcast interest just to discover. Otherwise, you can go to a rendezvous I mentioned earlier that MDNS is essentially they do the information discovery by having a server. All the other devices, services reported to the server, and you can go to the server to ask for the data, for the information. There's some flavor of a PubSub. Unfortunately, I'm running out of my time. I have to go very quickly now. So there's still a very much active research area. I really want to say something about,
What you're saying here really makes me think about DNS. So you say that we don't use DNS any longer, but what you are describing there is a bit the same thing. So I am still asking some kind of server, there can be lots of them. Can you give me things on that? What is it? And then it gives you back the element. So when you're saying that with NDN you don't have DNS any longer,
so the question is whether NDN still need a DNS server. Let's make it very clear. Today's DNS does the name conversion from application name to addresses. That's the fundamental goal here. But here, we're really talking about like a PubSub model where there's a rendezvous points, they collect the data, and whoever asks will get it, right? This is not a conversion from one namespace to another namespace. It's fundamentally different. If you ever manage the DNS server, you know the complexities. Like you look up CNN.com, what address do you get back? Well, it depends on where you are. Different users get different addresses back because none of the major the web pages actually served out of one server. So it's a very complex process just to figure out one name matched to which of the many addresses. For many, many different issues. There's also other means, like I talk about the sync. It doesn't require a server, but that's a too advanced topic. I'm afraid of adding confusions rather than a concept, so I'm gonna not talk about that. But end-to-end principle. Earlier, when I gave a talk, I think I gave a talk at the Matter earlier, and the question I got is, you threw the end-to-end principle out the window because you can get data from any other nodes. I want to tell you, in today's internet, there's very little end-to-end delivery now. There's so many middle boxes. There's the CDNs, there's the firewalls, there's this and that. You don't really go talk to your end server directly. To say that the one thing you care the most, when you do online banking, with whose server you actually set up an HTTPS connection. You believe you set it up with your bank. I tell you, 90% of the time or above, you are not setting up the connection with your server, with your bank server. You actually set up a box with a middle box. For what reason, I'll tell you later. But the NDN, you send the data by the producer, and then and the consumers can verify. So therefore, this actually reinstall the end-to-end principle, despite the fact that because of scalability, not everyone can talk to the true end server. And despite the connectivity challenges, you never had end-to-end connection at any time. But still, you can verify the data produced by the true server. So to summarize, NDN, after I talk all of this, just 3 simple ideas. Name data, secure data, then you have stateful forwarding. But the combinations of different ideas give you all the desired features that we've been looking for many years. You can do data caching because the data is named and secured. And with data caching, that allows you to do DTN, allows you to do fast loss recovery. With naming data and the stateful forwarding, you get multicast delivery covered. Because the stateful forwarding has this interest data exchange, right? So therefore, and also it has a state, so you can do multi-pass forwarding, and interest data exchange give you the feedback loop. You can do measurement that further fit into your multi-pass choices. And this is what Tamara mentioned earlier, that you can verify so that you can route around the malicious neighbors that give you the wrong data. You say, I'm going to go different interfaces now. So all this combination provides you the scalable, secure, and the resilient forwarding plane. There's many other features I haven't mentioned, but I'm out of time. This is my end slides. So Einstein said that we cannot solve the problems by using the same kind of thinking we used when we created them. Today's challenges come from how we do IP networking today. So therefore, if you want to address those challenges effectively, you have to think differently. And the NDN is present itself as a new protocol architecture to address those challenges so the internet can move on to the next 40 years.